Alright, so in this video, we are going to look at the principle of mathematical induction, or for short, PMI. We're going to look at what the PMI is and what it means for proofs in mathematics, and then we're going to do three proofs. The sum of consecutive integers is equal to n times n plus 1 over 2. And then this one down here, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 all the way up to 1 over n times n plus 1 is equal to n over n plus 1. And then we're going to prove that for all integers larger than 5, larger than or equal to 5, n squared is less than 2 to the n. These all may seem like obvious patterns or obvious facts, but we're going to prove them using this principle called induction. So let's get to it. Alright, so before we actually get to the proof of consecutive integers is n times n plus 1 over 2, so 1 plus 2 plus 3 plus all the way up to n, that ends up being n times n plus 1 over 2. Before we start doing this proof using mathematical induction, let's answer the question on what is mathematical induction, or the principle of mathematical induction, PMI. So we previously looked at how Gauss solved this problem. He took 1 plus 2 plus 3 all the way up to n, and he reversed them. He took n plus n minus 1 plus n minus 2 all the way down to 1, summed the two equations, and then was able to figure out that the sum of consecutive integers was n times n plus 1 over 2. But we want to look at that. We want to look at this proof. This fact using a different style of proof. Very often in mathematics, we want to show that a pattern is true, and not just from observation. So here's a famous sequence. The sequence f sub n, where the nth element in the sequence is 2 to the 2 to the n plus 1. This was a sequence proposed by Fermat, a famous mathematician, and he was looking at these numbers, and he didn't spend too much time on this, but he noticed that the first several elements in this sequence were all primes. If you plug in f of 0, you get 3. If you plug in f of 1, you get 5. If you plug in f of 2, you get 17. If you plug in f of 3, you get 257. All of these are prime. If you plug in f of 4, you get 65,537, which ends up being a prime number. But when you plug in 5, right, so prime, one might, with this sequence, assume that we're going to continually get primes, which turns out would have been a great thing for combinatorics. Cryptography. But if you plug in 5, you get 4,294,967,297. And that is a very difficult number to check if it's prime or not, to factor this. But it turns out that this is factorable. F of 5 can be rewritten as 641 times 6,700,297. Right? So in math, it's very dangerous to assume that something's true just because it follows a pattern, because that pattern may end up breaking. So Fermat's conjecture that this sequence here produced primes was proven false using a counterexample. But how do we prove something is true? And that's where induction comes in. So let's start looking at induction and what it means. Alright, so the principle of mathematical induction says, I've written it all out here, right? Let a sub n equal b sub n be a statement involving an integer n, such as what we looked at before, 1 plus 2 plus 3 all the way up to n, and how that equals n times n plus 1 all over 2. Alright, if a sub 1 is equal to b sub 1, meaning Is it true that 1 is equal to 1 times 1 plus 1 over 2? That's totally true. 1 is equal to 1 times 2, that's 2, divided by 2, that's 1. 1 is equal to 1. Right? If it's true for the first case, and if the kth case implies the kth plus first case, then this will be true for all integers. If a sub 1 is equal to b sub 1, and a previous case implies the next case, then this is true for all n. What this second one kind of means, and I think it'll make more sense once we do an example, right? If a sub 1 is equal to b sub 1, and I can show that a sub 1 equal b sub 1 implies a sub 2, and 2 implies 3, and 3 implies 4, and 4 implies 5, so on and so forth, then for all integers n, this statement that is given to you will be true. In my example here, I have the sum of integers is equal to the last integer plus 1 divided by 2. All right, let's look at this example here and really just kind of get into the nitty-gritty. All right, we want to prove that 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 all over 2. This is our A sequence, or our A expression, and this is going to be our capital B expression. All right. Is it true that A sub 1 is equal to B sub 1? That's what we need to do in order to prove that this is true for all n. All right. So we call this A sub 1 is equal to B sub 1 the base case. So step 1 when doing an induction proof, you want to prove the base case. And then we're going to show that the base case and then every case after that is true. All right, so is it true that A sub 1 is equal to B sub 1? All right. A sub 1 of the first sequence is just 1. It's that first term. And then B sub 1 is going to be 1 times 1 plus 1 all over 2, which is equal to 1. All right, so the base case checks out. All right, we are on our way to proving that this thing is true. All right, we have this inclination that this statement is true. We have reasons to believe it's true. We are proving it using the principle of mathematical induction. All right, the next step we call the inductive hypothesis. Right? We are going to suppose A sub k is equal to B sub k. Let me fix that k over there. We want to show that if this is true, suppose this thing is true. If it is true, is it true that A sub k plus 1 is equal to B sub k plus 1? All right. We want to show, is this true? That's the goal here. All right, so let me jump to a new color. What is A sub k plus 1? All right, we want to show that this is equal to B sub k plus 1. All right, the only thing that we have right now is the first case is true, and we are assuming that this case is true. Because if we can show this implication, then because 1 is true, 2 is true. And because 2 is true, 3 is true. And so on and so forth. So A sub k plus 1, that's equal to A sub k plus, so this is 1 plus 2 plus 3 all the way up to k. A sub k plus 1 is this plus the next integer. And this next step is where we use the inductive hypothesis, right? We know that A sub k is equal to B sub k. All right, and we have this k plus 1 just hanging out over here on the right, right? This is the thing that we said was true by assumption, right? I'm not saying that it is true necessarily, but if we can show that if this is true and it implies the next case is true, and we have the first case, A sub 1, if we can show that A sub 1 implies A sub 2, and then so on and so forth, we're golden. All right, so We have a sub k. We have b sub k plus 1. All right, what is b sub k? Well, b sub k is k times k plus 1 all over 2 plus k plus 1. And then what's this thing equal to? I'm going to put it right here. Do a little bit of algebra. So I'm going to multiply this thing by 2 over 2. And we're going to have 2. And we're going to have factor out a k plus 1. And we'll be left with a k plus 2. And this is b sub k plus 1, right? K plus 1 times the following integer k plus 2, all divided by 2. This is b sub k plus 1. We just showed that if the inductive hypothesis is true, and when you're doing an induction proof, you will use the inductive hypothesis at some point. That's the whole point, right? If this statement is true, then is the following case true? And in this case, it is, right? A sub k plus 1 is true because a sub k is equal to b sub k, right? And because of that, and because of our base case, because this is true, then, sorry, not b, a sub 2 is equal to b sub 2. And because of the inductive step, a sub 3 is equal to b sub 3. And this will continue for all positive integers. So we just have proven that 1 plus 2 plus 3 all the way up to n is equal to the product of n and n plus 1 divided by 2 using induction, the principle of mathematical induction. And the last thing I want you to do when you do these proofs is to conclude. So what have we done? All right, since a sub 1 is equal to b sub 1 and a sub k equals b sub k implies a sub k plus 1 is equal to b sub k plus 1, then by the principle of mathematical induction for all n, where n is an integer, a sub n is equal to b sub n. So go ahead and always finish your proof with some sort of conclusion statement so that the reader knows what you were proving in the first place. All right, what have you actually proven? We have proven that this statement, 1 plus 2 plus 3 all the way up to n, is equal to n times n plus 1 over 2 because the base case works, and because the base case works, the second case works, the third case works, the fourth, fifth, sixth, etc. Let's do 2 more just to kind of cement this in your brain. So here's another example. We have, and I already said this, 1 over 1 times 2 plus 2 times 3 plus 1 over 3 times 4 all the way up to 1 over n times n plus 1. And we're going to try to prove that that is equal to n over n plus 1. All right, so this first bit here, that's our a sub n, and this last bit here, that's our b sub n. Take a second to try to prove this using induction. Prove the initial case, all right, the base case. Then assume that the kth case works, the inductive hypothesis, and then use that hypothesis to prove that the next case works, and then you'll be done. All right, so go and try this one. I'm going to get started after you guys attempt it. All right, here we go. All right, does the base case work? I'm going to label it base case. All right, in this case, the base case is n equals 1. All right, so a sub 1, that's going to be 1 over 1 times 2. That's 1 over 2. That's 1/2. And b sub 1 is going to be 1 over 1 plus 1, which is equal to 1/2. So the base case checks out. Cool. All right, let's continue. All right, what's the inductive hypothesis? All right, we are going to assume that A sub k is equal to B sub k. Cool. And now that we've assumed this, this is something that we can use to prove that A sub k plus 1 is equal to B sub k plus 1. All right. If we can prove that implication, we're done. All right. So we know this thing to be true. Let's look at A sub k plus 1 and try to show that it's equal to B sub k plus 1. Right. This is our goal. So what's A sub k plus 1? Well, that's A sub k plus 1 over k plus 1 over k plus 2. All right, I've just replaced k with k plus 1. Right, and this is where we use the inductive hypothesis. A sub k is equal to B sub k by assumption. All right, I'm going to jump down over here. All right. Well, what's B sub k? That's going to be k over k plus 1. And we have this 1 over k plus 1 times k plus 2. All right. We're home free. We just need to show that this is, in fact, B sub k plus 1. All right. We need to show, and I like to kind of work in both directions, we need to show that this is k plus 1 over k plus 2. In other words, B sub k plus 1. All right, so we need to show that this right here is equal to this right here. And I'm going to take this to the next page because I've kind of run out of room. So I'm going to go ahead and take this to the next page. All right, we need to show that k over k plus 1 plus 1 over k plus 1 times k plus 2 is equal to k plus 1 over k plus 2, which is bk plus 1. Cool. So let's just do a little bit of simplification. Right? This term on the left needs a k plus 2, so I'm going to have a k times k plus 2 over k plus 1 times k plus 2. Over here we have a k plus 1 and a k plus 2 in the denominator. Now they have the same common denominator, so let's go ahead and combine everything. We have a k. I'm going to go ahead and distribute that numerator too. K squared plus 2k plus 1. You may notice why. And then down here I have a k plus 1 over k plus 2. Right? And that numerator factors. Right? That's a perfect square. So we're going to have k plus 1 squared over, there it is. Do you see it? The k plus 1 and one of the numerators, k plus 1, disappear, and we have a k plus 1 over k plus 2, which is totally equal to k plus 1 over k plus 2, which is b sub k plus 1. There we go. We have just proved that if the kth case is true, whether it is true or not, if the kth case is true, then the next case is true. All right, so what have we done? We have, all right, since a sub 1 is equal to b sub 1, and the first case implies the second case implies the third case, so on and so forth, and a sub k being equal to b sub k implies that the next case is true. Therefore, for all n, a sub n is equal to b sub n by the principle of mathematical induction. Very powerful, very true, very awesome. Let's do one more. Okay, so my final one I have for you here is a little bit different than the previous two. It is going to be the following, right? Prove that n squared is less than 2 to the n for all n greater than 5. Don't forget, when we're doing the principle of mathematical induction, we're dealing with integers. So n is, in fact, an integer. Cool. All right, so let's do this thing. After you kind of get the hang of mathematical induction, it's pretty straightforward. So let's see. This is my a sub n case. This is my b sub n sequence. Sorry, a sub n sequence, b sub n sequence. Is it true for the base case? All right, what's the base case? The base case is not 1 here. Right? The base case is n equals 5. All right, and is it true for 5? Let's see. Well, 5 squared. All right, 5 squared is equal to 25, which is, in fact, less than 2 to the 5, which is equal to 32. All right, so the base case works. The base case checks out. Sweet. Now we just need to make an inductive hypothesis, show that the kth case implies the kth plus 1 case, and then we are home free. Let's do it. Assume that k squared is in fact less than 2 to the k for some k greater than or equal to 5. It's obviously not true for things less than 5. You could just do a quick counterexample. All right, but assume that it is true for some k. Right? We need to show that k plus that fact being true implies k plus 1. So we are going to use the inductive hypothesis at some point. Right? So we need to show, or better yet, we need to prove that k plus 1 squared is less than 2 to the k plus 1. This is what we want to prove. And this is kind of where we're going to diverge from what we did in the previous 2 proofs. We're going to do this one a little bit differently. We're going to do it backwards, and then we're going to write a formal proof at the end. Right? We can call this like the discovery phase. All right, follow along. If I want to show that this is true, then that is the same as showing that x squared plus 2k, sorry, not x, k squared plus 2k plus 1 is in fact less than 2 times 2 to the k, right? Notice that I got this here. That's going to be useful, right? If I can show that this is true, then I've shown that this is true. All right, so we are going to do a sequence of moving backwards and then do a formal proof of moving forwards. All right, showing that this is true is the same thing as showing that I'm going to divide everything by 2. K squared plus 2k plus 1 divided by 2 is less than 2 to the k. Notice once again, I have that sequence right there. Right? I'm setting myself up here. Right? If I can show that this right here is true, then that is going to prove that this is true, because that's just algebra, and that's going to prove that the thing I want is true. So I need to prove that this is true. Let's keep going. All right, let me just take that last statement to the next page. We had k squared plus 2k plus 1 divided by 2 is less than 2 to the k. All right? And showing that this is true in this problem is equivalent to showing that this is true, k squared. All right? I want you to think for a second why, if this statement is true, if, I'm going to call this statement 1, if statement 1 is true, then statement 2, why is that the case? All right, think about that for a second. All right, this is the inductive step. This is the inductive hypothesis. All right, we assumed that k squared is in fact less than 2 to the k for numbers larger than 5. Right? So if I can show that k squared plus 2k plus 1 divided by 2 is less than k squared for numbers larger than 5 or larger than or equal to 5, I have shown it for 2 to the k as well. So that is my new goal. All right, and if I can show this is true, then I've shown this is true, and then I've shown that k squared plus 2k plus 1 is less than 2 times 2 to the k, and I have shown what I wanted to prove in the first place. All right, so we need to show that this is true. All right, so the first two examples I showed you in this video, pretty straightforward. Inductive proofs can be a little bit tricky. All right, they do require a little bit of intuition. All right, so we have k squared plus 2k plus 1 divided by 2. We need to show that this is true, that it is in fact less than k squared. So is this in fact true? Let's figure that out. I'm going to multiply by 2 on both sides. Once again, we are in this discovery phase. All right, I'm here. Now I'm going to subtract everything to the right-hand side. So I'm going to have k squared minus 2k minus 1. And that is larger than 0. All right, so I'm just moving everything to the right-hand side. All right. If this is true, we just need to show that this is in fact bigger than 0. Is that the case for k larger than 5? Well, here's a sneaky move. I'm going to add 2 and subtract 2. So I'm going to rewrite this as k squared minus 2k plus 1 minus 2. All right, why is that going to be nice? Why is that going to be useful? K squared minus 2k plus 1 factors. All right, I'm going to the next page. And so if you need to go back, just rewind. But I have now k minus 1 squared minus 1. Sorry, not minus 1, minus 2. All right, why does this do it for me? All right, I'm going to add 2 to both sides. All right, is this statement true? All right, is it true for k larger than 5? All right, if it's not immediately clear, all right, let's square root. All right, let's subtract 1. Sorry, no. Ooh, that should be a minus. All right, let's add 1. Square root of 2 plus 1 is less than k. Is this true? Absolutely, because k is greater than 5. Right? This is totally true. Root 2 plus 1 is way less than 5, and k is larger than 5. So we have shown a path. We have shown a path to success. Let's take that path in the correct direction as to prove that k squared is in fact less than 2 to the k for all numbers greater than or equal to 5. So I'm just going to go ahead and start this proof straight from the beginning. All right. So we want to prove that n squared is less than 2 to the n for all n greater than or equal to 5. All right, so base case. Base case. All right, is it true that 5 squared is less than 2 to the 5? All right, 25 is less than 32. All right, so we're good. Base case checks out. All right, inductive hypothesis. All right, assume k squared is less than 2 to the k for some k larger than 5. All right, this is going to be the money move later on. All right, what is true? All right, k, and let me write it over here, k is larger than 4, right? Right, this is the fact. Right, k is an integer and it's larger than 4. So k minus 1 is greater than 3. Right? We are using what we figured out earlier in reverse. Right? I'm going to square both sides. K minus 1 squared is in fact greater than 9. All right, and here it is. All right, we're setting ourselves up. We need this statement. All right, and this is totally true. All right, because this is larger than 9. Let me go ahead and write it. 9, which is larger than 2. So we have k minus 1 squared is larger than 2. And you can kind of see where we're going now. All right, let's expand. We have k squared minus 2k plus 1 is larger than 2. I'm going to go ahead and move the 2k and the 1 to the other side. So I'm going to get, what is that going to be? 2k plus 1. All right, I'm close to the perfect square here. I'm going to add k squared on both sides. All right, I'm going to factor and also divide by 2. That's a k right there. I'm going to have k squared is in fact greater than k plus 1 squared divided by 2. All right, and time to use the inductive step. All right, I know for a fact that k squared is less than 2 to the k for some number larger than 5. That was the inductive hypothesis. That's the thing that we assumed. All right, so this is in fact true. And I'm going to multiply by 2 on both sides. And I believe that we are done, because 2 times 2 to the k is 2 to the k plus 1, and we have just proven that the kth case implies the kth plus 1 case. All right, the big move here was right, where is it? Right here. All right, we assumed that k squared is less than or equal to 2k for some number larger than 5. Right? We're using the inductive hypothesis right here. And in every induction proof, you're going to use the inductive hypothesis at some point. Okay? And we set ourselves up so that we can move from a true fact. True. Right? Everything that it follows is true. Right? Then we use the inductive hypothesis, which isn't necessarily true, but we've assumed it to be true. All right? And because we get to this final statement, assuming the inductive hypothesis shows that the next case is true. And because the first case is true, the second case is true. Because the second case is true, the third case is true. The third case is true, the fourth case is true. It's kind of like dominoes. You knock one over and the rest will follow. Final step. Let's conclude. All right. So since a sub 1 is equal to b sub 1, and we have just shown that a sub k being equal to b sub k implies, or so in this case, let me rewind. This is a little bit different. Because a sub 1 is less than b sub 1, and a sub k being less than b sub k implies that a sub k plus 1 is less than b k plus 1, then for all n, a sub n is less than b sub n by the principle of mathematical induction. There you go. That, my friends, is the principle of mathematical induction. All right? If you can show that the base case is true and that the base case being true implies a recursive implication that the next case is true, then you're golden. Right? In this video, we looked at the green, purple, and blue proofs here, the induction proofs, but these things can get pretty mind-numbing. They can be challenging. The first two were pretty straightforward, just algebra. The blue one down here, though, n squared is less than 2 to the n for n greater than 5, that was a little bit different. You had to be a little bit clever in certain spots. You had to work backwards and then work forwards. So with that, I'm going to stop. I'm going to give you guys some problems to do to see if you can do them on your own, and then we will discuss later. Have a great week. Ooh, I totally realized I spelt mathematical wrong. Oh well.